Hi, welcome everyone to today's book talk on secondary electron energy spectroscopy in the scanning electron microscope by Professor Anjam Khursheed, brought to you by World Scientific. The event will begin shortly. Once again, welcome everyone. A few housekeeping rules before we start. Please have your camera off and your microphone muted throughout the event. There will be a questions and answers session after the talk. Feel free to post the questions in the chat box to Dr. Han Wei-Ting, who will be the moderator of today's event. Also, please note that this webinar will be recorded and posted online. Today, we are very good afternoon to those from Europe and good evening from those in Asia. Today, we are very glad to have Professor Anjam Khursheed with us. We also welcome Dr. Han Wei-Ting, who will be the moderator of today's sessions. And now I would like to hand it over to Dr. Han. Dr. Han, please.
Thank you, Sufan. A very warm welcome to this book launch hosted by World Scientific Publishing. My name is Dr. Wei-Ting Han, Research Fellow at the National University of Singapore, and worked together with Prof. Khursheed for, I would say, almost a decade actually. Yeah, so he's the author of the book we're featuring today. Prof. Khursheed has been working in the subject of SEM electron spectrometer attachments for over 4 decades. He started with designing voltage contrast spectrometers for the SEM back in, say, 1979, pretty long. Voltage contrast spectroscopy itself is an important part of secondary electron energy spectroscopy story. And it turns out that one of Prof. Khursheed's designs, the 1989 SE time of flight spectrometer could be one of the SEM inland spectrometers of the future. So Prof. Khursheed is one of the few researchers who have been working in the topic of electron energy spectrometers for the SEM. And the book being launched today is the natural combination of many decades of research work. Now, I would like to invite Prof. Khursheed to present to us some of the highlights from the book for us.
Okay, well, thank you, Wei-Ting. And I will now share my screen. And what I will be doing is I will really be just giving an overview of some of the highlights of the book. Can everyone see my screen? Yes? Okay, good. So I will just keep it to about 15 to 20 minutes. And really, I will go through just some pages of the book, giving an overview of what the technique can do. And first thing is that it's not really a widely known technique for the SEM, and the whole motivation for me writing this book is to try and publicize it more and get it out more into SEM users, and so that other people can start developing it and exploring it. First thing to say is that I'm sure you all know that the secondary electrons are the low energy electrons that are scattered back from a specimen when the primary electron beam strikes the specimen. There are a range of different scattered energies emitted from it, and the secondary electrons are usually the low electron EV electrons that are defined to be below 50 eV, but you know, most of what you collect from them are a few eV up to 10, 15 eV, but not too much beyond that. And so they're very low energy scattered electrons, the main electrons used for topographic imaging in a scanning electron microscope. Now, what's normally done in a scanning electron microscope is to use the secondary electron detector, which is usually in a conventional SEM placed to one side the scintillator is put at a high voltage and it attracts these low energy secondary electrons to form the topographic image as shown here. There's also the backscattered detector, which collects the higher energy scattered electrons. And usually the signal you get is mainly an SEM is designed to provide an image, and it's a bulk signal, a signal that's made of a wide range of secondary electrons emitted over different angles and different energies. And that's what I mean by a bulk signal. If we look at the energy spectrum, this information of the actual energy spectrum of the secondary electrons, where they peak at a few electron volts, go down somewhere in hundreds of EV are the Augers, and then up to the backscattered energy distribution. That kind of information, this spectral information, is not usually obtained in a scanning electron microscope. The two detectors that I just showed you don't average out and erase this kind of information. But the whole point of secondary electron energy spectroscopy is to obtain in parallel spectral energy information as well as the raw numbers that collection that give you the image information. So, of course, in material science, electron energy spectroscopy is very widely used and typically used for Auger electrons. And there are a range of different energy analyzers. This is the cylindrical mirror analyzer here. This is the hemispherical energy analyzer here. And they're used for Auger electron spectroscopy, X-ray photoelectron spectroscopy. And these techniques are very useful for materials analysis. On the whole, in the SEM, it's EDS as a technique that's used for materials analysis, but not scattered electron energy spectroscopy. So this whole book is about the fact that you can also use scattered electron energy spectroscopy to obtain useful information together with your image. Usually though, because there's very little space between the final pole piece and the specimen, just less than 20 millimeters or less, there's actually very little space to put in any analyzer. If you look at these analyzers, they're actually very big. Cylindrical mirror analyzer, the hemispherical analyzer, they come onto chambers, dedicated UHV chambers. To put in an energy analyzer in that small space inside an SEM is quite challenging. And I've spent a long time designing lots of different types of electron energy analyzers for the SEM. And in the book, most of the results are obtained by this toroidal deflector analyzer. It's an electric energy analyzer, and with a toroidal geometry, and it's made very, very small so that the working distance can be, say, less than 15 millimeters. So this is the energy analyzer attachment that I designed in 2008 and subsequently started to use for secondary electron energy spectroscopy. Now, I just want to give an overview of the kind of information that you can get with secondary electron energy spectroscopy. Here, in this case, we've obtained the spectra from different metal specimens. And what you can see is that apart from the yield information, you get information about the shape of the spectrum and how it changes with different materials. If you were, for instance, to plot the spectral peak height of each spectrum as a function of atomic number given here, you would see that there would be a linear relationship between the height change and the atomic number. That is very, when we obtained that, we were very happy and very surprised that the spectral height varies in this linear way, because the normal SE detector would, the yield you would get as a function of atomic number does not give any predictable, definable analytical relationship. So that it would be no particular relationship as given in this figure. But with SE spectroscopy, you get this very linear dependence with atomic number if you track the peak height. And this could be very useful for regions that, metal regions that are elemental, non-alloy regions on a sample, where you just need a quick estimate of the atomic number. And particularly useful, of course, for low voltage applications, LVSEM applications where EDS is not so effective. And for those things, so for material analysis, estimate of atomic number is one of the things, and I present a lot of that in detail in the book. Another thing is you can actually get the whole range spectra as well, right from the secondary electrons to the backscattered side by side. And there's a lot of information there. And how the backscattered spectrum changes with respect to the secondary electron energy spectrum, as the material, specimen material changes. And you can even start seeing fine structure appearing on the rising edge of the SE energy spectrum. And it turns out that this is actually indirectly interactions with the valence band electrons inside the specimen. I'll say a little bit more about that. So there's a lot of information there, and this extra information can be used for all sorts of applications, together with the backscattered spectrum as well. Another thing you might think, we were very surprised, but you might think that platinum and gold here are so close that, you know, you've got a linear relationship, but you can't distinguish them when you have very, very close atomic numbers. But it turns out that if you were to bias the specimen and increase your signal to noise, you actually get very reliable spectra where the gold is consistently, the peak is higher than the platinum, and the platinum peak is consistently broader. And if you use that information together and convert it into a kind of intensity, you can actually map, use it to map close atomic materials. Here's platinum. So this specimen that we used has platinum, aluminum, and gold. And we were able, from the SE spectral information, to identify platinum from gold with this kind of contrast, the blue and the red, near 100% contrast. In the normal SE image, you can't, of course, as expected, tell the difference there. If you look at the pixel intensity, you know, the gold and platinum in the histogram, they lie one on top of one another, but in the spectral, using this SE energy spectral information, they're very well separated. And if you look at EDS, this is all done at 1 kV. And if you look at EDS for the same conditions, this was as low as we went for our EDS windowless system at 2.5 kV. There's very little difference in the contrast in EDS, but the main point here is that with SE energy spectroscopy, there is a way of distinguishing between close atomic number regions on a specimen as well. The very sort of exciting thing, I think, of the book is the discovery that in an SEM environment, you can obtain valence band bulk density of states information. Here we obtained for tungsten an experimental DOS signal, and we've compared it against the DFT, a theoretical DOS signal, and they match very well. And the trick is to reduce the effect of contamination by taking different parts of your specimen and scanning over each different area faster and reducing the amount of time on any part of the specimen. And if you do all that, at 1 kV, you see the spectrum. At 500 volts, you begin to see these fine structures. And if you take them away and get a different signal, and then differentiate this different signal, you will obtain a very good representation of the density of states, the valence band bulk density of states of, in this case, tungsten. But I think we're one of the first, if not the first time, that this kind of chemical information has been obtained in an SEM, where you can match our signal, DOS experimental signal, to the theoretical density of states signal. I'd like to say that I got my inspiration that it could be possible from papers in the 1970s and early 80s. And those papers used dedicated UHV SE energy spectral systems. They don't make them anymore, by the way. These was just for research. You get very few dedicated UHV SE energy spectral systems. They're usually made for Auger or different applications. But in one of those, in 1979, they showed results that extracted these fine structures from the SE signal and matched them to peaks in the density of states, theoretical density of state signal. And but I think that we in the SEM, our method of using subtraction at different primary beam voltages actually goes further than this. This just matches the position of the peaks. But by that subtraction technique, and we are able to get rid of the cascade completely and obtain pure density, bulk density of state information. So I think this is very exciting application. It opens up a new area of applications for the SEM, and something that will go very nicely alongside EDS for low voltage SEM. Now I see that I've already got to about nearly 18 minutes, so I better be fast. A recent paper, by the way, will be published in Scientific Reports in about a month or two, where we also show we can see surface and volume plasmons superimposed on the density of states. Just to cover a few topics very fast at the end, we've also captured the secondary electron energy spectrum of a gallium ion beam inside a dual FIB and compared the energy spectra of the secondary electrons with that produced by an electron beam inside the dual beam. And you can see how much narrower they are compared to an electron beam. And that's characteristic of the, has information about the ion beam. It's also very interesting that you can map the areas that have been irradiated by a gallium ion beam with an electron beam afterwards using SE energy spectroscopy. So in intrinsic silicon, this is intrinsic silicon, we irradiated areas with a gallium beam, which locally dopes the specimen. Afterwards, if you go with the SE detector image with the electron beam, this is what you see, this kind of dopant effect of implanting gallium ions inside your silicon. This is what you get with the spectral, SE spectral approach. It's much more sensitive, and this is what you get with EDS. So, you know, our SE approach fares very well in terms of its sensitivity compared to the SE detector image and EDS here. And of course, it has obvious applications for the helium ion microscope. We haven't done that yet, but that's an exciting area. I see that I'm running a little bit over my time of 20 minutes, so I'll go very fast. It's a very useful technique for mapping dopant, p-n junction, dopant contrast, and in fact, space charge. This is a new discovery of the book, that we from a p-n junction sample, we were able to match very closely to the simulated space charge of a p-n junction. And so mapping buried space charge from p-n junctions is a new application, I think, for the SEM using this technique. And another thing in LVSEM that's very exciting is that you often go to low voltages to get a charge balance on non-conductors. Here we use the metal insulator semiconductor specimen that was fabricated with, these are metal regions. The blue is silicon nitride. And on the ordinary SEM image, this is what you see. It's operating at a charge balance condition of 1 kV. But when we use SE energy spectroscopy and get the spectrum for each pixel, you can start seeing the oxide is actually charging up. It's not apparent in your normal SE detector image, but using this spectroscopy, you can see and image the amount of charging going on. And if you carefully look and analyze how it shifts, you can map quite separately. These white areas represent areas that are charging up less. The blue is charging up more. And so you can actually image areas of a charge, the surface charge distribution on a insulator and under charge balance conditions. In the normal SEM image, you just see this. But what's really going on is that there's a surface charge distribution there. Last thing I want to do, don't have much time, I just spend a few minutes on this, is that also in the book, I present several methods going ahead for the redesign of in-lens SEM columns to incorporate SE energy spectroscopy. This is an idea I put forward for voltage contrast in 1989 using the time of flight principle, and that will give very good SE energy spectra. You have to pulse the beam, but if you can do that, it will give very good energy spectra. By the way, we do have in principle, that was published a long time ago, SE energy spectra from proof of experiments for that. And this one, we've also used and verified that it does give you good energy spectra. In the book, I present them as different column redesign proposals for in-lenses. And this is using a Wien filter. This is pure magnetic immersion. And there are two redesigning in-lens columns where you can bias and retard the beam at the last moment and have a magnetic field. And this one was proposed by Please and Kleinley. That was, I think their proposal was in 2004. And so the column can be redesigned for state-of-the-art in-lens column designs. And this is a proposal I worked on, where you use a magnetic beam separator. The SEM column comes in this way, and the secondary electrons, scattered electrons, are scattered back out the other way and energy analyzed. Anyway, the book contains these proposals, and really the challenge is that I think what my book suggests is that in a conventional SEM with the toroidal attachment, you can get lots of very interesting new lines of applications for the SEM. And if we were to redesign these in-lens SEM columns to also achieve SE energy spectroscopy, we would also get, you know, very good benefits as well. But that's a challenge for the SEM engineers to do that. And so I think I'll just finish. I've gone 6 minutes beyond my allotted time, but I'll go back and stop sharing at this point. And back to waiting.
Oh, thank you, Prof. Khursheed, for insightful talk. Yeah, it reminds me of a lot of the work we have done for the past few years. Yeah. And now we'll be moving on to the panel discussion. And I would like to invite our first panelist, Professor Cornelia Rodenburg from the University of Sheffield, England, to say a little bit about the topic of SE energy spectroscopy in the scanning electron microscope. In particular, the opportunities and the challenges, and any questions she might have for the author. Prof. Rodenburg was one of the first to propose energy filtering inside in-lens SEMs around 20 years ago, and has been working in relation to this SE energy spectroscopy in the SEM for many years. Professor Rodenburg, please.
Okay, thank you, Weiding. Well, I know there is very much excitement about what is in the book in relation to density of states in metals. But what I find most interesting these days is working on polymers and protein structures, and that we can, of course, also find valence band information there, although we don't have comparison to simulated data because they're not available for these structures. But practically, we can actually map functional groups, and you can look out for a paper in Advanced Science appearing soon for quite a number of different polymers where you can see those functional groups and what energy ranges they're located in. And so I'm very excited about this because it allows us to actually do nanoscale mapping. In fact, we have shown you can improve the resolution by energy selection as well. So we can really do nanoscale mapping of functional groups in really complex materials, polymers, proteins. But you probably notice that these materials are also very beam sensitive. So we can actually do this with very small beam currents. And this is a big advantage and a great opportunity I see in these kind of materials. For another application where I'm really excited by the book, I liked very much the presentation of the SE spectra generated by ions, because of course in ion microscopy, the chemical analysis is still a big challenge. And this might be the obvious solution. And not only that, also it has opportunity because you showed that you actually put it in a dual beam instrument. So that means you have an electron beam and an ion beam. So you can actually build structures or you can etch away structures. And the SE spectroscopy using actually the ion SE spectra gives you an in-situ monitoring instrument of what you're doing. When you build structures, you can control the quality of your structures. If it has a high chemistry, you can actually see if you're causing too much damage. So in fact, you can have feedback loops and control your building and etching processes much better than without such in-situ control. And EDX simply does not deliver that information. So we find, for example, for carbon, we can see if we have sp2 or sp3 bound carbon, and it matters a lot because one is conductive and the other is not. So I see a lot of opportunity in those dual beam instruments as well. So yeah, I'm very excited about what we see in our materials, and it goes very well what has been just reported in the book about the matters. Altogether, I think secondary electron spectroscopy has a very bright future. We call it slightly different in my group. We call it secondary electron hyperspectral imaging because we concentrate a lot on the imaging and actually mapping specific energy windows for specific functional groups, as I just mentioned, because for material scientists, this is really important. And it kind of competes with Raman spectroscopy, only we can do it in an SEM without actually putting a Raman spectrometer in there. So yeah, I'm very excited, but I have a few questions in relation to those opportunities. The first one is, so you demonstrated that you can actually collect these ion-induced secondary electron spectra in a dual beam instrument where you use gallium. But of course, the biggest opportunity are in a more recent dual or multi-beam instruments, really, where you have like helium ions or neon ions, or even oxygen or nitrogen ion sources. So what do you think is the future for these kind of instruments? And can you make sure that we can collect SE spectra in those kind of instruments?
Yeah, I think so. I think that there's a good opportunity. In fact, I think it would be actually easier to do in those instruments than in the dual FIB instrument. The procedure will be very similar to what we're doing in an SEM. You just put the spectral, the energy analyzer attachment onto the specimen stage, and put your specimen inside that little unit, and the whole thing will sit on the specimen stage. And I mean, in our particular setup, we haven't got any little specimen movement, but you can, once this takes off and we put more effort into it, you can also move your specimen about in the normal way as well. So yes, I think it's quite straightforward, quite doable. As long as you stick to SEs in that energy range of tens of EV, you're fine. It's quite easy, straightforward.
Okay, so that's excellent news. I have another question, and that is when you showed all those spectra and the fine structure, that is really the exciting bit that you can see. But signal to noise obviously is an important consideration in this, and you touched on this by biasing the specimen.
Yes.
But another important thing for the signal to noise is actually your electron source. So could you just comment what type of electron source or ion source might be required?
Actually, you know, for our work, we actually did not find too much difference between an ordinary tungsten source or a field emission source in terms of the spectra, and that is, I think it very much depends on the actual energy resolution that you're getting with the secondary electrons. The spectrum itself is not really limited by the energy spread of the ion source, for instance. The energy spread of the electron source or the ion source is only important for the primary beam imaging. But our secondary electron energy spectrum, the shape of it, the fine structures, we didn't see any limitation coming from the actual electron or ion source.
Okay, so that's good news as well. So you may actually use it as an analytical tool, or if you want an imaging tool, the field emission gun, obviously. Yes. But if you want a nanometer resolution.
And the other thing that maybe in relation to your question, because you're calling it, what do you call it, hyperspectral?
Secondary electron hyperspectral imaging.
Okay, in my book, I call that spectroscopic imaging. But we do a lot of this spectroscopic imaging because it's quite easy to form images at different energies. With our kind of bandpass analyzer, of course, the energy window is down to tens of milli-eV. I mean, it's very, very narrow. So you can form very exciting and very interesting images. And that's how we were able to form those kind of charge map distributions. And so it is very exciting to develop that.
Yes, we need those very narrow images if you want to
Yes.
look at protein structures, for example,
Yes.
to distinguish the
Right.
peaks are actually quite close together,
Yeah.
and many
Yeah.
of them.
Yes.
So that's why we call it hyperspectral imaging, because we collect actually stacks of like hundreds of energy ranges.
The very exciting thing is to combine that extra spectral information together with the imaging.
Yes.
And that's the exciting thing, I think. And then it would be something comparable to EELS, which combines imaging information with spectral information. And I think that's the best thing to aim for.
Yes, and we're actually already doing that, however, not in a perfect way, because we still rely on a built-in systems that is accessible to us in our microscopes. So my last question is with regard to future design, because you introduced the time-of-flight instrumentation there, and that would be very, very good design for the kind of materials we're talking about, protein structures, buttery materials, organic solar cells, or solar cells in general, where actually the beam can cause damage, and EDX is utterly misleading because you actually destroy your material while you analyze it. So these kinds of things would obviously benefit from the pulse beam you require if you use a time of flight.
The time of flight, I did experiments in the early 90s now, but we really got very, very fine good signal to noise SE energy spectra from it. And the good thing is, there is automatic current dose control inside there, and that would be good. It would be a very accurate way of doing it. And I just want to say that this is kind of up to the SEM engineers, I hope, that are listening in for this evening.
That was my final questions. Have you actually managed to convince any manufacturer of your time of flight?
Well, you know what I found was that I was working for a long time. A lot of my work was done on designing electron spectrometers and different designs, and no one was actually reading those papers. And that was my motivation to write the book. I thought it was more important to show what an SE energy spectrometer could do to convince people it was worth investigating. And now I think if they are convinced, then we can get, you know, SEM engineers now involved and developing systems like the time of flight. I give about 4 systems where proof of experiments have worked for inland systems. So it's a case of now making them commercial.
Okay, well, thanks for answering my questions, and sharing the excitement.
Thank you.
I'm looking forward to see some of your designs available to the material scientists.
Okay,
Okay, thank you so much, Professor Rodenburg. Yeah, and I see that a lot of the participants here are very active in asking the questions. So if you still have a question you have not asked, please send it to me privately on the chat down below. And I'll at the end of this talk, when we have the time for the Q&A, we will be going through some of the questions. Okay. So now I would like to invite our other panelist, Dr. Philip Meeker, who has been working in the Institute of Scientific Instruments in Brno, Czech Republic, and to say a little bit about the topic of SE energy spectroscopy in the SEM. So it's actually, I've met Philip for quite a few years. I think it was 2017 when you visited our lab, And since then, he and his colleagues have been greatly helped to our research by supplying a lot of very useful test specimens, and also contributed significantly to the work reported in the book. So in September, Philip also organized an international workshop on the topic of secondary electron energy filtering in the SEM, where we also met Prof. Rodenburg for the first time. So without further ado, I'd like to invite Dr. Philip Meeker to give his talk.
Okay, thank you, Wei-Ding, for a nice introduction. My name is Filip. Hi, I'm from Czech Republic, as was mentioned, and I'm working in the field of scanning electron microscopy almost 15 years already. And when I first met Anjam in the recent Trends conference, I find out that by accident I'm doing also the secondary electron spectroscopy, because we called it in our institute also a different way. We are dealing with the low energy electrons and with the imaging in the so-called cathode lens. So we are playing with the low energies, and we are imaging the non-conductors inside the scanning electron microscope, and we are trying to resolve the angular and energy distribution of the secondary electrons. And now our topic is to analyze mostly the organic pigments, which comes from the cultural heritage preservation, and we are also dealing with the imaging of dopants inside the semiconductor. So I think the book, which will be shortly available in the market, is very interesting for us, because it's touched so many topics that we deal with. And mainly I'm very excited of the spectra of different kind of materials, because it's nice that you can obtain the results same as in EDX with a very low energy and very high accuracy, and also without any side effects like contamination or so much irradiation of the specimen. So yeah, I would like to ask the Anjam also for some questions, if I may. The first one will be about the kind of database which is probably in progress, and I would like to ask you about if exists some database of the secondary electron spectra for some elements in the scanning electron microscope.
At the moment, not from the scanning electron microscope. There have been, of course, secondary electron energy spectra published and reported from dedicated UHV spectral systems in the past. Mm-hmm. And there's been a lot of variety in all of that. But we from this book, we have analyzed about 8 or 9 different elements, and we certainly in the future will analyze more and make them available gradually. I think that we're the only ones in the world at the moment that actually are producing SE energy spectra from an attachment like this in the SEM. We've supplied one at the moment to just a collaborator, but we're really at the very beginning, and I think it will take some time to compile this database.
Yeah, I think that will be really important for the users of the scanning electron microscope to have some comparison, some database of what they are able to see, not only the material contrast with the secondary electrons, but also some kind of spectral information inside these images. And the second question, I read in the very end of your book that you are trying to make the analyzer improvement in a way that you will be able to see the angular distribution of the secondary electrons. Can you a little bit comment about?
What I do at the last chapter is that I talk about more instrument improvements. One thing I think that will be quite interesting is to obtain in parallel the angular distribution of the secondary electrons. Together with this energy distribution, I think you will have more information about your material, and they can be used together, because certainly the energy distribution will depend on the emission energy, emission angles as well. In our toroidal spectrometer, you know, it's only plus or minus 8 degrees around a 45-degree emission. But I think if you quite separately capture the angular distribution, I think you will have, together with the energy, a lot more options.
Yeah, you will got the complex complex information about your electrons which are coming from the sample. And it's very important if you are using not the initial energies around 1 keV, but if you will start to use the 100 eV primary beam energies, then it will become really, really important. So I'm very pleased to hear that it's possible, and I put my finger crossed to you to put such an instrument in the market. So it will be really really useful for the people who are working with a scanning electron microscope to put such an attachment to the scanning electron microscope and improve the ability to have the spectral images inside the regular SEM. Okay, thank you very much, Anjam.
Thank you. Okay, I think at this point, I would like to invite Wei-Ding to say a few words, or, you know, about 5-10 minutes, because Wei-Ding, as he's already said, has been working with me for nearly a decade now, using this, using electron energy spectrometers, and he did his PhD on this subject. And he's now a postdoc with me, and with all that hands-on direct experience, Wei-Ding, what are your thoughts?
Yeah, so in the beginning, when we talk about spectrometry or spectroscopy inside the scanning electron microscope, yeah, for the decade, much, especially the first few years, the big difficulty is how do we overcome all the different factors that scanning electron microscopes always give us, because the usual things that happen in a high vacuum environment, like contaminations, like beam current, like charging. How do we even track charging? And through all these problems that we face, and through all this investigation into the problems, it somehow extended into a series of different applications that we found out, like the MIS charge tracking, like being able to track contaminations through the carbon OJ peak, or even just or mitigating carbon contamination effects of the spectra. All these things have been, it's been like a series of steps that we've carefully done our work to investigate and mitigate all these different issues up to this point where we have finally achieved this spectroscopy and I think this all is due to the fact that that it is not impossible to be done in a scanning electron microscope, but a good design of a spectrometer is needed, and a good series of work has to be done at the start to investigate all this, so that we have found out the properties, so future users of SEM don't have to. So they'll know which parameters to use, which beam, what kind of samples is suitable for which kind of parameters. All these are, and I think for the future, this technique could be extended to many materials. And we've been talking in a group, and perhaps maybe in the future we might even do more fanciful materials, 2D materials, or functional materials, things like that. Yes.
Okay. Okay. Good. Good. Okay. So I know at this point there have been many questions from our listeners, and so I'd like to hand it back to you, Wei-Ding, because I think you've been keeping your eye on the questions, right?
Yes.
So,
yes, sir. Yeah.
Why not let's get into the Q&A. We've already had 50 minutes so far. So
Let's see. Yeah, and I apologize for not being able to go through all the questions. There have been quite a few, so I'll just pick some that we can do within our time. There's about 10 more, 15 more minutes left. So perhaps, Prof, the first question is, I think Peng Han would like to know for the applications that we have talked about, what kind of spectral resolution do we need, and I guess they are interested to know what kind of resolution that we can achieve in the SE spectrum.
Right. Okay, so the actual thing, in chapter 2 of this book, I go into a lot of detail on signal to noise requirements. And the interesting thing about SE energy spectroscopy is that it's very different from, say, Auger or XPS, where you do need a high energy resolution. We're using an energy resolution for a bandpass energy analyzer that's actually not that great. It's only 2.5% for our toroidal energy analyzer, but 2.5% at, say, an energy of 1 eV gives you 0.025 eV resolution. So the resolution that you don't need a high resolution, and anything under 10% relative energy resolution is good enough. And so you can open up your exit slit and really have a high signal to noise ratio. That's by far the much more important consideration rather than energy resolution. Unless, of course, you get to 50 eV or 60 eV and you get higher in energy. And this is because the energy range is so low, less than 15 eV, say, that the relative energy resolution you need is not that much. You will get a very small energy window, and you're more concerned about getting enough signal to noise. So we're not limited by energy resolution.
I see, sir. Okay, let's see. Next question. Let's see. Oh yes. So Ben Todoff would like to know, because one of the diagrams in the primary beam column, you have shown a monochromator in the design, and he's wondering whether it is needed.
Okay, well, I propose a monochromator for 2 of my 4 proposals, and those 2 proposals are pure magnetic immersion proposals. It turns out, for instance, the time of flight proposal is that you don't want to accelerate the secondaries as they go back up. So you will not bias your specimen negatively. And so you need your secondaries to drift slowly back up to the detector. And that is why that scheme uses a pure magnetic immersion lens without biasing your specimen. And in order to preserve good high image spatial resolution at, say, a landing energy of 500 eV, you do need a low energy spread from your gun. Or you could also employ a monochromator. using a Schottky source. So that's why I put a monochromator in for 2 of my in-lens proposals for spectrometers. Those 2 use pure magnetic immersion lenses, and to get good image resolution, you need to lower the energy spread at, say, very low landing energies like 500 eV.
I see. Okay, I see, sir. Okay, let's see. Okay, maybe I think this question will be applicable to all the panelists as well, because this is something that I think we all face a lot, like which is so Wu Jiang has a question. So he asks the kind of effects that beam current has to the SE spectrum, and I think this question, the answer to this really depends on the type of material. So, and all the panelists are working with all the different type of materials that the beam currents do have an effect on. So maybe we can take around starting from Philip.
Okay, so beam current is can be really destructive for some materials, as you mentioned. But I think with a high beam current, you can also get the nice signal to noise ratio. So you have to carefully think about what current you need to use. It's always nice when you can play with a little bit and try from the picoamps to the 100 of picoamps, for example, and you still have the signal. That's really nice on the secondary electron spectroscopy, that you can achieve your energy window even with the picoamp current. That's my experience in this.
I see. How about Prof. Rodenburg?
Yeah, the kind of materials we look at, beam current is absolutely crucial to keep it down. And definitely we only ever use picoamps. Even for the imaging, it's also important that you really use very fast imaging. Because otherwise you can destroy your materials. Or the other thing that happens is you build up contamination. It's probably something that is overlooked because normally you don't see it, but if you collect SE spectra, of course you see immediately if you do build up contamination, or indeed if you damage your specimen. So that's one huge advantage of a SE spectroscopy. You know when you do something wrong in your imaging, because if you have too large beam current, you see the contamination growing in your spectrum. If you actually lose your fine structure, you also know you have too much beam current because you amorphize your sample, which is very easy to do with protein structures, for example. So that's why SE spectroscopy is great, because you know when you do something wrong. It's an excellent control measure to know what you're actually doing and what you should avoid. So to optimize your image, the SE spectroscopy is really useful.
Okay, and I'd like to add that we were using tens of picoamps for most of our spectra. And we were getting signal to noise ratios on height change and standard deviation of the spectrum. We were getting signal to noise ratios of easily over 50. So we were getting good reliability on the spectrum for tens of picoamps. And but I'd like to reinforce what Connie just said. One of the really important things about SE energy spectroscopy is it gives you this extra added information beyond the image. So if there is something strange going on, like you've got image contrast reversal, or there's charge appearing on the surface that you can't see in your SEM image, you get a lot more extra information about what's actually happening. So beam current is very important. It very much depends on your application. How much beam current, it's always a trade-off between signal to noise and not damaging and things like this.
But theoretically, for the inexperienced user, the spectrum, if it can be collected and processed fast enough, could be a feedback loop that helps you to optimize those things without having to think about too much, because it will alert you if there is a carbon buildup or if your spectrum changes.
Yes, yes. And in fact, with SE energy spectroscopy, you can actually track your carbon peak anyway.
Exactly.
Quite independently.
Okay, so maybe a couple of questions since we're running out of time now. From Alberto. Oh, Alberto. It talks about the time of flight spectrometer, which is very exciting. But I could, Prof. Khursheed comment about the time resolution that could be achieved and the electron pulse duration required to achieve it.
As long as you are in the pulsing into the nanosecond or sub-nanosecond, it doesn't have to be much below a nanosecond pulses. You can arrange your column to have the lower energy electrons can drift for hundreds of nanoseconds, typically under 200 nanoseconds. The experiments I did had very nice spectra over about 200 nanoseconds. I think it was, now I remember 20, 30 centimeters of drift length. And what was the other part of it?
The electron pulse duration. You need to.
The electron pulse duration, yeah, these widths are in the region of nanoseconds or sub-nanoseconds.
I see.
And of course, the big issue is the duty cycle, because you will have to wait for, I think you only need about 100 nanoseconds and to pulse on widths of about a nanosecond, typically is to give you good spectra. But something I'm working on is to actually blank your specimen on and off by plus 10 volts and look at switching changes. And if you can switch fast, you may still get your very high current and go between secondaries and backscattered, and the switching and the time analysis between it may give you all that information as well. So there are lots and lots of ideas you can do with time of flight.
I see. Okay, so let's see, maybe one final question since we're right on time at 9. Yes, actually, but this other question would be to, he's also very interested in defects and morphology. So he's asking whether it's possible to detect or obtain information about defects in semiconductors.
That's something we've talked about, and that's a very exciting application of the density of states, because there are things like defect density of states, and something that we have yet to explore, but the density of states information has the potential, I think, to do it, and we would really like to explore that.
Well, in gallium nitride semiconductors, for example, I've shown, like, I think in 2002, that you can actually see the dislocations in there, and you can see whether they're charged or not. Clearly in a spectrum, or even if you just use an energy filter to actually image the appropriate energy region. So yes, you can map defects in that way.
Right, good.
Okay, thank you so much. I think that's all the time we have for the questions today. Thank you so much. I think and thank you everyone for coming. I'll pass it back to Sufan.
Yeah, hi. Thank you, Prof. Khursheed, Dr. Mika, Dr. Rodenburg, and Dr. Han for your sharing today. We encourage everyone to give this new book a read. For more information on the book, do visit World Scientific website, and also sharing the screenshot, which you can just use the QR code to scan to the book page. And we are now having 30% off, so the promo code is available on the screen. So we have now come to the end of today's webinar. It has been a delight having all of you. Goodbye. Thank you.
Thank you.